Thanks for coming. Thanks for having me. So this is a joint work with Sam Drews, who's the student leading this project, Loris D'Antoni, who's other faculty member working on this at Wisconsin, and Aditya Nori, who's at Microsoft Research. And I'm Aws. All right, so this is Alan Turing. If you've seen the movie, you probably remember that he is pretty smart. In 1949, he wrote probably the first proof of a computer program. So he wrote a program that is a sequence of instructions, and those sequences, that sequence of instruction had to compute the factorial of a function. Okay? And he said, all right, so I've written these sequence of instructions. How do I prove that it actually computes the factorial all the time? And then he went on and he sketched out a proof of correctness, that the program always terminates. And when it terminates, it actually produces the factorial of a number. Okay? And it's a very nice paper. It's somewhat unknown, but you should look at it. It's pretty cool. And then ever since that proof of correctness, as we started building computers and building sophisticated programs, we've been investigating what it means for a program to be correct. So in the 60s and 70s, we built logics for reasoning about programs. In the 80s and 90s, we built automated tools. And in the 2000s, we kept building more and more scalable program verification and analysis tools. And in most of those cases, we've been verifying or checking properties that Turing proposed. Things like the program should always terminate, the program should not divide by 0, the program should return the result it is expected to return. So the properties have always been Boolean. Either a program is correct or not correct, for the most part. Okay? But as we move forward towards the 21st century, which we are in, by the way, the reach of programs is expanding. So programs are almost everywhere. They're doing all kinds of things. And the notion of correctness is really fuzzy. What does it mean for a program to be correct, other than not crash and return the right result? What is the right result? So let me give you an example. A recent example, for instance, is Facebook. So it was tinkering with our timelines. You've probably heard about it. They were doing some kind of A/B study to see how people react to different news stories that show up in their timeline. For one group of people, they showed negative stories on purpose. And for another group of people, they showed positive stories, just to see how they react. What do they post after they've seen such things? Is the program correct? Is the timeline program correct? Well, it didn't crash for me. Facebook was working flawlessly. Everything I tried to do worked just fine. But think of perhaps the people who were maybe on the brink of suicide, right? And they got a whole day of negative tweets or Facebook posts. Maybe some of them committed actually suicide because of that. Okay? Is the program correct? I don't know. Right. So other again, instances where a program employed at a massive scale can affect us is algorithmic pricing, where an algorithm determines the price to give to a consumer. So it's been shown by a bunch of investigative journalists. There's a bunch of articles about not only Amazon, but other online stores as well, where certain areas, perhaps certain zip codes, which have a lot of minorities living in, disadvantaged minorities, tend to get higher prices for some reason, because the algorithm decides, I don't know, that's the best thing to go with at that point, if you log in from such a zip code. Okay? Is the algorithm correct? I don't know. Okay. So more serious cases, there's this very nice article from ProPublica, a nice piece of investigative journalism. So there's this software that is being used in courts in a bunch of states, including the state of Wisconsin, where I work and live, that takes a person's information, so a person who committed a crime and is about to be sentenced, and it sort of predicts if they're going to commit another crime in the future. And according to that score, the judge might decide on different sentences. And it's been shown that this software is biased towards against African Americans, even for some very simple crimes compared to, say, a white person committing a much more serious crime. It would say, oh, this person will more likely do more crimes in the future, and as a result, perhaps will get more significant sentences. Okay. So this is one of the problems with deploying programs at scale, societal problems that might arise. And many questions have been asked, many articles have been written, many papers have been written, and recently even books on the question of discrimination and what do we do about it in the 21st century when so many of our decisions are being computerized and algorithmized, if that's a word. All right. So the question I'm going to ask in this talk is, how do we prove, and what does it mean, to prove that a program does not discriminate? Okay? So in most of these instances and most recent sort of works and media attention has been on bureaucratic processes. So we're making hiring automated, mortgage rates are automated, sentencing is automated. But you could imagine in the future where, say, we have autonomous agents like robots running around, helping us out, they could be biased themselves. Okay? So the problem is really general, and I'm going to look at it in this talk. Okay. So we're not the first people to work on it. As I said, there are theoreticians who have been asking, what does it mean for a program to be fair or unbiased? Machine learning people have been asking the question as well, asking what does it mean to build a fair classifier? So if you're doing some classification on a set of data, I want to generate a classifier that is unbiased. Security and privacy researchers, as well as some investigative journalists, have been trying to find bias in black box algorithms like advertising algorithms by bombarding them with data and trying to find some statistical significance. Even legal scholars have been asking questions about how do we hold algorithms accountable, and if there's an algorithm that is biased or algorithm that is doing something that is detrimental to the society, who is accountable for that, and what do we do about it? How do we regulate it? And in fact, in the EU, for instance, in 2018, there will be regulation against algorithmic decision making. So if you are a subject of a sensitive decision that is made by a computer, then they need your consent. And if if you say they decided not to hire you because of some algorithm, then you have the right to explanation. I don't know what that means. I don't know how they're going to employ it. There's just legalese. But you could imagine you're asking the question of what part of my input or what part of which attributes of mine made the algorithm behave this way, or which execution path I took through the code, effectively. In the US, we don't have any regulations, but there are a couple of White House reports, one from 2 years ago and one from this year, which talk about big data and things like that. But they say something like powerful algorithms raise the potential of encoding discrimination, automated decisions, and what can we do about it? So in this talk, I'm a programming languages person, verification person. I'm going to begin by viewing fairness as a property of programs, just as, say, termination or not dividing by 0 is a property of programs, not crashing. Okay? And then in the second part of the talk, I'm going to talk about how do we automatically prove or disprove fairness of a program. Okay? So let's begin with the first part. Okay? And please ask me questions at any point. So this is a program D that decides, say, whether to hire you or not. And the input to D is a vector V, which is a bunch of inputs, a bunch of arguments to D. Okay. And H is a Boolean variable. It's either true or false. It decides whether to hire you or not to hire you. Okay. And we're going to assume that V, as I said, is a vector. And one part of the vector over here is what we're going to call the sensitive attribute, okay, for now. So it says whether you are a minority or you're a majority. So we're just going to assume that the population is divided in half. There are people who are a minority. There are people who are non-minorities or majority. Okay? And what I want to prove is that the probability of hiring a person under the condition, so hiring is true, under the condition that they're a minority, divided by the probability of hiring a person under the condition they're not a minority, is greater than 1 minus epsilon. Okay? So what does this mean? This means if my population looks like this, 10% of the population is a minority, and I get applications uniformly from this population, then the composition of my hiring, the people I hire, will be at least 10 minus epsilon minority or more. Okay? So I don't care about overrepresenting minorities. I just care not to underrepresent them. Okay? If you want to ensure equal representation, then you could add an extra less than here. Okay? Yes? Yes. Making everything else the same. What do you mean? No, I'm just conditioning on whether someone is a minority or not. So it's sort of like I restrict the population to minorities, and I say, okay, what is the probability that I hire a person from this group? And then I restrict it to majority, and I ask what is the probability. Okay, so these two things are independent as far as I'm concerned. Yeah. Yes. Yeah. Yeah.
In the zip code example, there's a flag there's a point at zip code.
Correct.
And then there's whether the person is a minority or
Yes, yeah.
They're two separate entities.
Absolutely.
But zip code actually tells you what.
Yeah, yeah. So here, as far as I'm concerned, D may or may not access the fact that you're a minority, but it might access other things that are correlated with that, and we'll get there. Okay. Yeah. Other questions? All right. So this is a simple program that we're going to use throughout the talk to decide whether to hire a person or not. Okay. So it takes a person's college ranking, the rank of the college they went to, the years of experience that they have, and their ethnicity. Okay. So the first thing it says, oh, look, if the person is from a top 5 college, and I'm going to hire them right away. Okay. So you guys are in luck. Otherwise, I'm going to look at the years of experience they have and subtract the college ranking. Okay. So if you've gone to a lower ranked college, then you need more years of experience to make up for it. Okay. And if that number is greater than -5, then I'm going to hire them. Otherwise, they won't be hired. Okay. And what I want to prove, for simplicity, everything here is real valued. Okay. So I'm going to assume ethnicity itself is also a real value. And a person is a minority if their ethnicity is greater than 10. Otherwise, they're not a minority. This is just to make the math look right, okay? Because I don't want to mix booleans and reals, and then it gets pretty weird. All right, and higher here is boolean, but don't care about it for now. All right. So let's see. So one thing to notice here is that this program does not access ethnicity at all. Okay? Doesn't know. We just have it as an input just to say that we know something about ethnicity in this problem. Okay? So what we're going to assume is that we have a model of the population. Okay? So we have a probabilistic model where people, applications, or applicants are drawn from this probabilistic model. Okay? And this probabilistic model might tell us something that people of a certain ethnicity probably go to lower ranked school because they're disadvantaged, so on. Okay. All right. So the question is, how do we define this population model? Okay. It's a probability distribution, but what does it mean mathematically? Okay. So the way we're going to define a population model is we're going to have a probabilistic program, or a program that can draw from probability distributions, can draw random values. And you can think of this program as if it's like a random generator of people. The more likely a person to occur in the population, the more likely it will be generated by this program. And their features will be correlated in a similar fashion. Okay. So let's look at a very simple program like this. A person's ethnicity will be a Gaussian, centered at 0 for some reason, to make this example look nice. Their college ranking is a Gaussian centered at 25, so it looks something like this. So most people go to a college, ranked 25 or so, give or take 10. And years of experience, most people have 10 years of experience for the sake of illustration. And then if a person's ethnicity is a minority, if the person is a minority, then their college ranking will be shifted a little bit. Okay, so they're effectively drawn from a Gaussian that is centered at 30 in this case. Okay? And then I return that person. And what I have on the other side is the decision-making program. And effectively, this program is producing people, and this program is deciding whether to hire them or not to hire them. So to the verification folks in the crowd, you can think of this as a probabilistic precondition. So it's just a precondition typically is a formula most of the time that defines the legal inputs. Here, each legal input has a probability of occurrence. All right. So this is, again, the verification problem. This is the precondition. We draw something from the population, or someone, I guess. We decide whether to hire them or not, and we want to prove that this inequality holds. Right. So this is a conditional probability. We're just going to rewrite it as follows. And I'm going to say, use min to denote that ethnicity is greater than 0. The person is a minority. Right. So effectively, in order to prove this inequality, or to disprove it, we just need to compute the probability of this event, this event, this event, and this event, plug them in, ensure that they're greater than 1 minus epsilon. So for illustration, I'm going to look at how do we compute the probability of this event over here, hiring someone who is a minority. So let's characterize what it means what this probability means in our model. So what we're saying is that what is the probability of the population model generating a person who's a minority, and then the decision-making program to hiring them. Okay? So what is the probability of these two events occurring? So effectively, we need to reason about the composition of these two, the population model, which is a program that generates an applicant, and the decision-making program, which is the program that decides. So we're reasoning about the composition of these two programs. Okay. So formally, let's say pi is the set of all possible executions, concrete executions. So pi will have a set of all possible executions. Each execution is a run of the population model, where it generates a person, and then a run that takes that person and decides whether to hire them or not. Okay, so this is all possible executions that I have over here. Okay. And then let's assume that each such path has a probability associated with it, a probability of occurrence of that execution. So now it's pretty simple. I could just look at all the paths, the subset of paths over here, where a person is hired and they're a minority. Okay. And in order to compute the probability that a person is hired and the minority, I just sum up the probability of all those paths, the paths where a person is hired and they're a minority. Essentially, just take each path here, take its probability, and sum them all up. Okay. So that's how you compute it. All right. But I assume that all my inputs are real valued, so I cannot just take the sum, because there is uncountably many paths. Okay, so this is really an integral over the set of paths, whatever that means. Okay, so I guess the next question is, what does this mean? How do we formalize it? Okay. So let's go back to our population model. If you think of the population model and you think of the decision-making program, the only part where there's non-determinism is over here. Okay? Those three values that I get. Everything else is deterministic. Once I fix those, the program just runs deterministically, and I know what it's going to do. So each path, effectively, each execution path, is uniquely defined or uniquely characterized by three values. Okay? So essentially, each path is characterized by a point in three-dimensional space. So if you were going to take all the paths where someone is hired and they're a minority, you can think of it as a region in three-dimensional space. Okay. So now the probability of hiring a person who's a minority is just taking this region phi, okay, and integrating over this region, which is a region in 3 dimensions, where each point in that region is weighted by the probability density function of ethnicity, the probability density function of college rank, and the probability density function of years of experience. Okay. Everyone's on board so far? All right. So this is the problem that we're solving, and it's a weighted volume problem. Okay. So we're computing the volume of this region weighted by some probability. Okay. So the simple version of this problem is just the volume of phi. Effectively, each point in phi has weight 1, has the same weight or uniform weight. In this case, each point has a different probability of occurrence. So in our running example, if you look at phi, phi is a formula over college rank, ethnicity, and years of experience, and it looks something like this. Okay. So if your college rank so each point here is a point is an input where a person is minority and is hired. Okay, so if you can see, if the college rank is below 5, then a person is in this region and therefore is hired, right? As soon as your college rank increases, or you've gone to a lower ranked college, then you need more years of experience to make up for it. Yeah.
So this only works like if there's no ifs or whatever.
No, actually, you can have ifs and you can have whatever. It can be arbitrarily complicated. So what we're assuming here implicitly is that all statements in the program are polynomial assignments or polynomial inequalities. Okay? So you can pretty much model a lot of machine learning classifiers like support vector machines, decision trees, neural networks with linear units, and things like that. Okay.
But you do need some processing in the program to complete this region, right? I mean,
right. Yeah. So. Yeah. Yeah. So I'm gonna assume I don't have any loops. Although one way to handle them is to keep unrolling and looking further and deeper and deeper into the program. Yeah. So for now, let's just assume there are no loops. But otherwise, I can have any polynomial assignment or polynomial inequality in an if statement. Yep. Right. So the reason you see this, it's sort of like a composition of two shapes, and this is because of the if statement, right? So they have this case where a person their college rank is less than 5, and the case where their years of experience minus their college rank is greater than -5. And each of these is just the probability density function that represents the probability distribution. So in this case, the years of experience are Gaussian centered at 10. So we just take that formula and plug it in there. So then the question is, how do we define phi? Right? Okay, phi is the representative of each execution path that satisfies the property that we're interested in. And the way we do that is as follows. Okay. So these are the two programs that we have. We can represent each program as a formula. For the verification people, this is really just verification condition generation or bounded model checking. Okay. So this program over here, we're going to define a formula phi pop. Okay. So in this case, for instance, this if statement over here is represented by this implication. It says if this is greater than 10, this implies that college rank 1 is equal to college rank plus 5. Okay. So I shift the college rank. And these subscripts and superscripts are static single assignment form. You don't have to care about it. Okay. And notice that the probabilistic assignments do not show up in my formula. And then the decision-making program, similarly, I can encode it as a formula. All right, so it's also encoded as a formula. You don't have to care about it much. It's pretty standard construction. So now I define phi as follows. I take the conjunction of the two programs. I compose them. Okay. So every model of this formula is an execution that goes through the first program and then goes through the second program. Now, I'm only interested in executions where a person is hired and a person is a minority. So I'm just going to restrict these to be person that is hired, person that is a minority. And then the next thing I'm going to do is I'm going to quantify out all the deterministic or non-probabilistic variables. Okay? So I'm going to say, OK, the program has so many variables, and I'm only going to focus on the ones that are probabilistic, because that's what defines phi. So everything else, we're going to project out everything else. And I'm going to project down on the three-dimensional space that is college rank, years of experience, and ethnicity. Okay?
In this example, is there anything else?
Well, there's these programs, there's these things where college rank 1 and so on. We can throw them out. So there's like auxiliary variables that show up. All right. Other questions? All right. So to recap, want to compute this. We characterize all executions phi as an SMT formula or a first-order formula. And then we want to compute the weighted volume of phi in order to compute the probability. And this is what the weighted volume looks like. So the volume of a single polytope, if everything is just linear inequalities, is a sharp p-hard problem. Here we have exponentially many polytopes, potentially in the size of the formula, because each execution path would be a polytope, or even not even a polytope, even worse. And we're not only computing the volume, we're computing the weighted volume. All right. So this brings me to the next part of the talk, which is how do we compute this probability automatically. Right. So this is, again, the problem at hand. We want to compute the weighted volume of this region. Right. So the first thing we observe is that if the region is rectangular, okay, in two-dimensional space, let's assume, then the y values will be distributed according to some distribution. Everything in this talk is Gaussian, but the problem is more general, or the setting is more general. The x variables will be, again, distributed according to some distribution. Then to compute the weighted volume of this shape is really just high school math. You just compute the area under this curve, compute the area under this curve, and multiply them together. Okay? And that's the weighted volume of this rectangle. But of course, our shape is not rectangular. It could be just arbitrary. Could have arbitrary faces. Yes.
And that is because they're independent.
Because they're independent, right? Yeah. Yeah, our formula is arbitrary. But what we could do is we could break it down into rectangles, right? Definition of integration. But there are infinitely many rectangles, right? So you could just keep breaking it down, chopping it up into smaller and smaller and smaller pieces, and you'll go on forever. So what do we do? Well, we're verification people. We're not scared of infinity. We battle infinity all the time, so we're just going to live with it. All right. And this is exactly what we're going to do. So the insight, or the main technique, is going to go after this problem in 2 steps. So the first thing we're going to do is we're going to characterize the infinite set of hyperrectangles that live in the formula. And I'm going to say hyperrectangles because we're working in higher dimensional space. We're going to represent them all as a formula. And it turns out we can actually represent that infinite set of rectangles as a formula compactly. And then we're going to start sampling rectangles that are inside that formula. In the limit, we'll converge to the actual volume. Okay. So that's the story. All right. So let's start by hyperrectangular decomposition. Or actually, let's illustrate how the problem actually will look like. So starting from a shape like this, we're just going to keep sampling more and more rectangles, okay, until we've covered enough and gotten a good bound to the actual volume. So let's talk about decomposition. Again, decomposition, we're trying to characterize all possible rectangles inside the formula as a new formula. Okay? So let H be the set of all hyperrectangles that are inside of phi, okay? The infinite set. Okay? Now, we're going to construct a formula called the decomposition of phi, okay, where there is a one-to-one correspondence between the elements of H, all the hyperrectangles in H, and the models of the decomposition of phi. Okay? So each model in this decomposition uniquely characterizes a hyperrectangle, and each hyperrectangle that lives in phi is uniquely characterized by one of these models. Okay? And it took me a long time to find this symbol, but I was very proud of it. It's pretty cool, I think. Yeah. So let's see how we're going to do it, how we're going to define this cool symbol with an equally cool formula. So this is what we're going to do. First of all, we're going to quantify out all the variables in phi. Okay? So we're going to take all the variables that show up in phi, and we're going to universally quantify them. So these are all the variables, right? And then for each variable in phi, we're going to create a fresh new variable that's called the upper bound of that value, and a lower bound. Okay? So if you just look at this part of the formula here, this part, it's really just defining a hyperrectangle, right? Assuming I plug in constants over here. Okay? And I'm going to say this hyperrectangle should live inside of phi. And of course, yeah, so these are upper and lower bounds. And each upper bound should be greater than the lower bound, obviously, just for sanity. So now, the only free variables in this formula are the upper and lower bounds. So any model of this formula is going to be a rectangle that is inside of phi. Okay? Pretty simple. So everyone's happy with this construction? Okay. Yes?
You say for each variable independent. Okay. But if you quantify universally over the variables.
Right, yeah, because I want validity, right?
For every variable individually.
What's that?
And then you make another convention over each variable individually.
Right, because I'm saying give me an upper bound.
In that,
yeah.
Oh, I see. Okay, yeah.
Because you want an upper bound along each dimension. So if you have just 2 dimensions, you want an upper and lower, upper bound on lower bound on the x and the y. The opposite.
So if phi has 3 variables, this calligraphic x phi is x1, x2, x3.
Right. Yes. Yeah. Mm-hmm. Does that make sense? Do you want further illustration?
Yeah,
Get a board.
I think that's okay, but the free variables are. Yeah, the free variables are lower and upper bounds.
The free variables are the lower and upper bounds. Yes. Okay. So any model will be just telling me an upper and lower bound for each variable, for each dimension, effectively.
So why do you call it a hyperrectangle? Oh, because it's in many dimensions.
Yes, it's in more than 3. Yeah. All right. So now that I have this decomposition formula, I can go and actually sample from this formula. Okay. So here's what the algorithm is going to do. First, we're going to assume that the volume is 0. Okay? That's where we start. The volume is absolutely 0. We know nothing. Or the weighted volume in our case, not only volume. Now we're going to get a model of this formula, just a random model. Well, we just call this a SMT solver. There's no notion of randomness. Okay. So just a black box. We ask an oracle for a model. It gives us a model. Now what we can do is we can compute the volume of the hyperrectangle that is defined by this model. Remember, the model will define a hyperrectangle. Okay? And we know that this was easy. I mean, this is why we're actually decomposing things into rectangles, because we know for rectangles, it's easy to compute the volume. Right? And now I can just keep doing this. Right? So getting more models, get more rectangles, get more rectangles, get more rectangles, and then keep growing my volume. Except that if I get a rectangle that looks like this, the next time I want to ensure that a new rectangle doesn't overlap with it, so that I don't overcount the volume. So what I need to do is I need to stipulate the next time that any new rectangle should be either to the left, to the right, above, or below. Okay? So I'll add a disjunction that says anything new should be on one of the sides. If you have more dimensions, then you'll have more sides. Okay? So it's sort of like we're breaking up the search space the next time around, as Marcus suggested yesterday. All right. So we can. I'm not going to go through this encoding, but it's a pretty simple encoding. All right. So if we have something like this is our original formula. After a few samples, we might get something like this. Okay. So here we have one big hyperrectangle, then a bunch of hyperrectangles that are making up this ladder shape. The more we sample, the more better resolution we get on this pixelation of the original shape. Yes.
So if you're getting a model from a black box, how
right.
do you ensure that sequentially you are getting sufficient area with each iteration?
What could go wrong? Right. Yeah. Great question. Yeah. So what could go wrong, right? I mean, we're not sure. We are just getting models from a black box, and it could be adversarial, right? So what could happen? Suppose we have a shape that looks like this, just 2 dimensions. We have a rectangle, triangle, okay? Too many rectangles. And then we could the black box could just keep giving us unit rectangles, just like single points. The weight of a point or the volume of a point is 0, okay? And just keep, I will diverge or not stay in my place. Alternatively, suppose most of the probability is concentrated up there, right? I could just keep getting sampling low probability regions over here. I could keep getting rectangles that live inside of here forever, right? There's infinitely many inside of here. I could keep getting them. Okay? Again, I will diverge. So what do we do about it? So ideally, we would do something like this. We not only get a model inside of the decomposition of phi, we want a model where the hyperrectangle that is defined by that model has maximal volume. Okay? I want the biggest thing ever at any point. I don't want to cut any corners, literally. But this optimization problem is pretty complex, right? I mean, here the volume of a rectangle is just the multiplication of a bunch of cumulative density functions, which I cannot give to an LP solver, I cannot give to an SMT solver. No one's going to solve it for me. It's an arbitrary formula. Okay. So instead, what we came up with is the following. We said, OK, we're going to approximate the density function. So given a density function that looks like this, like a Gaussian, I'm going to approximate it with a histogram. Okay? Could be just an arbitrary approximation. No guarantees are required on what this approximation looks like. Now,
doesn't have to be a lower bound.
It can be anything. Yeah, it doesn't have to be a density function. And now, what the area under a histogram is actually, we can represent it as a formula in linear arithmetic. Okay? So I can actually compute, if you tell me compute the area from here to here under the histogram, then I actually can represent that as a formula in linear arithmetic. Okay? And I'm not going to go through the instruction, through the construction. Yes?
In the previous slide, wouldn't you simplify and consider the unweighted
Correct, yes, yeah. So you're saying
And
just...
then compute the weighted volume. But to
Right.
count, to cover it, you don't need to consider the weights. It seems to me, I don't know.
So you're saying just compute the volume of the triangle?
Yes.
Without any
Without
weights?
weights.
Okay.
So then it becomes an ILP against?
No, I don't. I mean, so you compute the volume. Now you get a single number. You know, it could be like 100.
No, you don't compute the volume.
Uh-huh.
You compute the rectangle.
Uh-huh.
And then another, but it's a big rectangle, right?
Okay.
But you want
Right. It's a big, yeah, okay. So
and
you're...
then you compute the volume.
Yeah, I mean, which is kind of what we're doing. I mean, so if you go back to the algorithm, we just get any rectangle, which is defined by a model.
Right.
And then we compute its volume and add it to the sum.
But here you don't maximize.
I don't maximize, right, yeah.
But go to slide.
Right? Over here? Yeah, here.
Yeah, here.
Yes.
So instead of using the real volume with the weights,
Yeah.
why don't you use the unweighted volume?
I see. Because the unweighted volume will still might still give me rectangles that are large or maximal, but in zero probability areas, or very low probabilities.
That's fine, but still, by keep doing that,
Yeah.
you will cover the whole thing, right? And then you compute the weighted.
Right. Yeah, so we tried something like that, and it didn't work out in practice. And as a result, we said, okay, we want to find large, but not only large, but highly dense. And that's what the next construction is trying to do. Yeah, so as I said, the area under a step function that looks like this actually turns out to be a linear formula. So now we can encode, roughly speaking, the volume. We actually don't maximize the volume. We maximize each side of the rectangle, because maximizing the volume is nonlinear. Turns out to be pretty complicated. So we approximate it by maximizing each side independently, or making sure it's larger than some threshold. And one thing to note is that, again, you can use any approximation you like. Okay? In this case, you get fast convergence in the sense that you need a small number of samples to cover a large region, but the sampling is slow, just because encoding a very precise approximation like this gives you a large constraint to add to the formula. In this case, convergence is slow, meaning that you're getting rectangles that are roughly good, but not very good. But sampling is fast because you don't have any complex constraints in the formula. So you have to pick a trade-off. In practice, we just fix one kind of approximation. We don't dynamically change anything. Okay. Everyone's good so far? All right. Right, so properties of this algorithm. First, it maintains a lower bound on the volume. You can stop it at any point. You know that the volume is at least that value you have so far. It converges to the actual volume in the limit, modulo some little things that you have to take care of. This works for real closed fields, meaning that if you have polynomial inequalities, it will work. It'll be very slow, but it will work. So every step of the algorithm that I showed is actually decidable. Now, to compute an upper bound, in addition to a lower bound, we can just negate the formula. Okay? So the volume of phi is equal to 1 minus the volume of its negation, right? So if I want to compute an upper bound on this, then I could just use this inequality. I'll call the algorithm simultaneously on the negation. This gives me an under approximation or a lower bound. And then 1 minus that gives me an upper bound. Okay? So I can run the two threads simultaneously. I'll get a converging lower and upper bound. All right. All good? Cool. So let's go back to our original goal, is to prove fairness, or a property that looks like this, that we consider as a good proxy for fairness. And what I showed you is an algorithm that computes a lower bound on a probability that looks like this. Right? So if I want to prove that this ratio is greater than 1 minus epsilon, then what I'm going to do is I'm going to compute a lower bound on the numerator, an upper bound on the denominator. This gives me an under approximation of this ratio. If this under approximation is greater than 1 minus epsilon, then it's definitely greater than 1 minus epsilon. Okay? Now, alternatively, if I want to prove that it's unfair, then I do the opposite. Compute an upper bound, lower bound. This is an over-approximation of the ratio. If the over-approximation is less than 1 minus epsilon, then it's definitely less than 1 minus epsilon. Okay? And therefore, the problem is unfair, or the program is unfair. So this is what we're going to do. Just employ the algorithm that I showed to compute a bunch of probability of a bunch of events simultaneously. So we implemented all of this in a tool called FairSquare for obvious reasons. And I can show you a demo of the tool. So, right. So what I'm going to do is I'm going to run the tool on the example that I've been talking about throughout the talk. Just going to say demo. Takes a while. So this is the 1 minus epsilon, right? And I'm simultaneously getting an under-approximation that is growing and an over-approximation on the ratio. Okay? So if this goes below here, then we definitely know that our algorithm is unfair. See? Yeah. That's what happens when you give grad students intellectual freedom. Right. Okay. So what we're going to do is we're going to go into the program and try to fix it to get rid of this unfairness. So where did it go? It's over here. So it's kind of written in some hacky version of Python that we came up with. So if you recall that we had this constraint that says you take the years of experience and subtract the college ranking, it should be greater than -5. What I'm going to do is I'm going to sort of diminish the power of the college ranking, and by increasing the weight of the years of experience. So effectively, I'm going to just multiply this by 5. Okay. So I'm saying if you have a little bit of years of experience, it completely outweighs the college rank. So any subtraction won't matter much. Okay. But if you're from a top 5 college, you're still guaranteed a job. So you guys are still lucky. And I'm going to run this again. So now things tend, to be pretty fair, I guess, or hovering around 1 minus epsilon, and eventually, so I think epsilon here is 0.1 in this example. So we're just proving that, we're not very different from the majority of the population. And at some point, we're going to break this threshold. Come on, come on. Yeah, all right, not racist. That's good. All right. So this was the demo. We actually ran it on more realistic examples. So we took some data set that people in machine learning have been playing with in terms of trying to figure out fairness and unfairness of classifiers. And what that data set does, it talks about salaries of people, whether they get a high salary or a low salary. And the correlation, the sensitive attribute is whether you're a male or female. So here we generated a bunch of decision trees, which, given your information, decides your salary. A bunch of support vector machines, a bunch of neural networks, very simple ones, and then we had some population models. Okay? So in the first row here, you see completely independent inputs. So each attribute of the applicant is completely independent of all other attributes, and as a result, the program is fair, because there's no correlations whatsoever. And then as we introduce correlations, we see that some of the programs or some of the classifiers we prove as fair or unfair. And the time it takes varies drastically, just because we have pretty heavyweight machinery, SMT solvers and so on, that sometimes, for instance, quantifier elimination over here takes a lot of time, and then we time out. What's that? Seconds. Yeah. And sometimes, this timeouts after, I think we put it at 800 or 900 seconds, but we still get a lower and upper bound. Right, and these two programs here is we sort of encoded a primitive form of affirmative action, where we took, for instance, decision tree 16 over here, which was unfair, and what we did is we flipped a coin if the person is a minority, and with a probability of 15.15, we would hire them anyway, even if they're not. We would give them a high salary, even if they're not given a high salary. Okay, just to sort of try things out like that. And similarly, a support vector machine here, we added that affirmative action, and we again proved them fair after we've embedded that extra condition. So current and future work, we're looking at the problem of how, given a program that is unfair, how do we repair it with a small shift? So we want to maintain that the new program is very close to the original program. We're assuming that the person who generated the original program is not trying to be adversarial or biased. So we want to just shift it a little bit and make it fair. One problem with volume computation is that if you have a slanted region, as you saw, you'll need very many pixels effectively, or just high resolution in order to cover that region. So we're looking at rotating the formula in order to get just rectangles that are orthogonal to these regions, or parallel to these regions. And then we're looking also at randomized volume computation, or thinking about doing something about it, where you get some probabilistic guarantee on the volume that you've computed so far. So that's pretty much it. I talked about logic, probability, and justice. Probably the greatest three concepts that we've come up with so far as a species. That's all. Thanks. Yes?
So naively, if I had to integrate some nasty function over a weird place, I would just do Monte Carlo something.
Right, yeah. So Monte Carlo works, but if the probability is very small, then you'll need exponentially many samples potentially to get a good bound. But yeah.
I mean, so can you sort of maybe say something about in which case the one might be preferable to the other?
Right, yeah.
I can't guarantee with Monte Carlo, but lower bound numbers and so on.
Right. So let's see. So when looking at, say, inference in a Bayesian network or a probabilistic program, if you do sampling, just forward sampling, then you can get an epsilon delta guarantee, meaning that that you're an epsilon away with some probability at the end. If the probability of the event that you're trying to measure, especially with conditional probabilities, is very small, then you'll need potentially exponentially many samples. So people end up using things like MCMC, Metropolis Hastings, which does not give you any guarantees whatsoever. I mean, it gives you guarantees that in the limit you converge to the actual probability, but you never know where you are typically. So if you use things like Church and Stan and those ones, they employ, these probabilistic languages employ something like MCMC. So in our case, we get a hard guarantee on the probability. I don't have probabilistic guarantees. And I get an upper lower bound, and I know that I converge in the limit. So I get more guarantees than those tools, and I'm not really sensitive to low probability regions because I'm directly sampling, getting hyperrectangles or samples within the regions I'm interested, within the events that I'm interested in. But if something has low probability in Monte Carlo, you'll probably keep sampling forever outside, or you might need a lot of samples before you get a representative description of that region. Yes.
Can you combine these ideas?
Yeah, that's, I guess.
Like tilting the distributions for sampling based on TSO2 stuff.
Yeah, I mean, that last part in the future work was the randomized algorithm, which has some of that flavor with some guarantees as well. Yeah. Yes.
So how would that definition work with the ratio that you had if you had, like, let's say 5 groups of 20%?
5 groups. Then I would just have all the, yeah, you mean like the greater than, right? I mean, you could say that they're all, yeah. You could say that they're all an epsilon away of each other. I don't know. I mean, you have to come up with a definition. Again, we're freestyling here. This is not like, doesn't come from God as a definition of justice. So someone came up with it. But I mean, one thing you could do is you could say they're all equal. Modulo some epsilon, and then maybe give some order to those people. Or maybe there's a majority and a bunch of other minorities, different minorities, but a single majority group, and you want all of them to be an epsilon away from the majority. Yeah.
So right now you are approximating like rather complex sets as boxes, right?
Correct. Yes.
So these sets are not polygons. Can we also
So,
polynomials inside them?
Yeah, in theory, our algorithm works for polynomials. In practice, all the examples I've shown are linear. So, convex polyhedra, yeah.
Yeah, polyhedra.
Yeah.
So have you tried to have suggestion maybe for you something you can
Yeah.
I remember there is a formula in which you have the Q that implies phi.
Correct.
Right?
Yes.
And then you try to eliminate the quantifiers ahead. So you have this formula.
Yeah. I mean, technically, you don't have to eliminate the quantifiers if you have a solver that can deal with quantifiers.
Yeah.
But we do it for practical purposes.
So have you tried to solve the formula phi a priori? And so if you have linear constraints, you will have a linear system that represents all the solution for that formula, right? For phi.
Well, so say that again.
So yeah, if you apply your the quantifier eliminator on phi.
On phi itself.
Yeah, on phi itself.
But phi, I mean, quantifier elimination removes everything from phi. Which formula are you talking about? Maybe we should just go back. This formula here?
So yeah, if you have x appearing phi, right?
This x. So all of these are all the variables inside of phi.
Okay.
Yeah.
So if you let them free and you eliminate the variables inside phi, then you will have all the solutions. So all the combination of age, ethnicity, and college, such that satisfy that formula, right?
Well, that's what phi is to start with. That's how phi is by construction.
So phi by itself is already a polytope.
Or a union of polytopes.
Oh, union of polytopes.
Yeah.
So how about trying to approximate that set directly without passing through this formula here, like using some linear optimization, linear programming techniques, for instance. So you can fix some directions of simpler objects, like a box, an oriented box, a parallel, or whatever.
Sure.
And then you can try to push the facets of this object towards the edge of the points that satisfy the
Right, which is what we're implicitly trying to do by saying, give me the dense most rectangle, right? We're trying to push it to the boundaries. And not only we're trying to push it to the boundaries, we're trying to find one that is in a region of high probability.
But my intuition is that maybe using linear programming, you can tackle larger problems than using a series of SMT, right?
Right, yeah. I mean, the problem is that, let's see. Yeah. I mean, the problem is that here we have a set of polytopes. So for linear programming, we'll have to pick a polytope. And then the question is, how do you pick?
It's only one by one.
Yeah, but I mean, there could be exponentially many. And then you could say, start with the most probable polytope by maybe first running the program, see which paths are more likely, and then taking those, and then finding. And then the problem is that how do you sample inside of the polytope, right?
Yeah, if you have a simple object, then it's easy.
Right.
You don't want to approximate that polytope with another polytope, which is
No, yeah. So, but I mean,
if you have another box or an oriented box.
Yeah. Right. But you need. I mean, one thing that we try to do first is to just take a point that is close to the mean of all the distributions, and then build a polytope around it by expanding to the as much as we can. But then that turned out to be not a good idea because. Think of something like this. So maybe this is your polytope, something like this, right? And then maybe this is the most probable point, okay, according to our distributions. So we get this point and then try to build something around it, right? So maybe I'll go this way, and I'll get this region, right? Okay. Right. So there's so many possible rectangles that can live around that point. And perhaps even though we started with the most probable point, that doesn't mean we're going to build a good rectangle around it. So by using our technique, then perhaps the dense most rectangle is this one. Even though it doesn't include the point, it might have more density overall. So we end up getting this using our technique because we're.
Yeah, what I had in mind was related to the directions rather than picking a point and then trying to inflate the box around that. So.
Yeah, the problem is that.
I have the impression that maybe there are some numerical approaches that are like. Okay.
Yeah. I mean, we tried to do something like that, but that wasn't good enough. Then we switched to that. I guess yes and yes.
So you're assuming that you have like a generative model of the population.
Correct. Yes. Yeah. How
would you take that into account in your procedure?
Yeah, so I assumed that someone gave me a generative model and assumed that is the best truth we can get so far.
I mean, like, of course, like, it'll be impossible to actually determine, like, the true difference
Right.
between that and, like, the actual distribution.
Uh-huh.
Like, if that were given, then would that somehow, could you incorporate that into your
Well, I could.
feature, like, give, like, conservative bounds on, like, how
Mm,
how many samples you need or something else?
right. Yeah.
Yeah, like, it might be involved in, like, say, like, how robust this algorithm is.
Right. Yeah, I mean, we've been thinking about something along those lines, but in a different setting where, say, the population is shifting over time, and I want to ensure that my decision procedure is robust to changes in the population. That it will be unfair. It will be fair for the next 10 years, and assuming that we get lots of skilled immigrants and things like that, you know. But we still don't have a good solution. So. And yes, you had a question.
Yeah, I mean, can you comment? I guess it's a follow-up on this question. So this notion of justice or fairness
Yes.
is essentially depends on the population, right? So in
Yes.
some sense, you are maybe the unfairness is already in the population model,
Uh-huh.
and
Right.
you're trying to correct this by having an algorithm that doesn't reflect this unfairness blindly,
Yeah.
but with the shifting the weights around tries to correct this, right?
Yeah.
Anyhow, I mean, I don't see any other way of doing it, I guess, but since you know about this area and
Yeah.
I know nothing except this talk, is this notion of fairness well established in the community?
There
Or are many debates of what is fairness mean?
There are many debates, even in philosophy and law. There is no.
In this context.
Yes, I mean, so in this context, there are actually even more debates, and I learned that the hard way. So one thing that could go wrong in this. So let me tell you first, actually, where this comes from. This definition that I showed. Maybe let's go back to see where this definition appears. I don't know where it went. Yeah, here it is. Right. So this definition is inspired by the Equality of Employment Commission. So they say that if you're hiring from a certain religion or ethnicity or race, you want to make sure that 4/5 or 80%, the representation is 80% of the minority versus the majority. Okay? So take the most represented group, and any other group should be 4/5 of that representation. So in this case, if you put this at 0.2, then you get that 4/5 rule. So again, that is a rule that is not necessarily employed in court. It's just a recommended rule of thumb, more or less. So we took this from a paper that was trying to formalize that rule of thumb. Now the problem with such a definition is that what it says is that I just need equal representation. So suppose you guys at Berkeley are giving out scholarships, full ride scholarships at the beginning of the year, and you say, oh, look, we gave out scholarships with an equal representation. Okay, so the percentage of people from the minority group got the same, is the same as the percentage of people from the majority group. But what you could do to hack this property to make it true while not being really true is to give the least qualified minorities scholarships. Now they go to Berkeley, they fail in their first semester or first year because they couldn't handle it, and they drop out, and then you take the rest of the money and you give it to the majority. Right? You were fair, but not really fair. So what people have proposed are other notions of fairness at the level of individuals. So this is called statistical parity or group fairness, where we're comparing the outcome of two different groups at the level of groups. But individual fairness says two people who are alike, again, for a definition of alike, should receive similar outcome with perhaps a high probability. But then the problem is that what does alike mean? It could be that people who are in the minority group and the majority group are not comparable in the alike, so no two people are alike. And then you could, using that definition, you could just not hire any of the minorities. So there's this, competing notions, and some people are pretty passionate about it. Yeah.
In relation to that, I mean, the legal framework is much clearer, I guess, than the ethical framework.
So the legal framework is actually not very clear because.
For example, you're not allowed. I mean, as far as I understand, you're not allowed to make decisions based on the protected characteristics.
Right. Yeah. I mean, actually, there's this notion in law in the U.S. of disparate impact, where you disparately impact a group of, a subset of the population, and that actually started, or the main case, if you study that, if you just Google disparate impact in Wikipedia, the main case started where a certain, I think, steel factory or something in the South decided, okay, all workers should have a high school degree, even assembly line workers who don't need a high school degree. And most of the African-American populations there did not have high school degrees. And as a result, suddenly they couldn't work at that factory and was a major, a major employer. So over there, they didn't discriminate according to race, but according to an attribute that is not necessary for the job at hand, but indirectly impacted a large part of the population. But even given an excellent population model and a tool like this, my understanding is that statistical arguments do not hold up in court. So they're not considered evidence. But, according to a legal scholar I talked to, for free. Other questions?
Thanks.
All right, thank you.